In this lesson, we'll talk about division of polynomials. First, let's recall how do we divide a polynomial by a monomial. That means by a single term. Well, the idea is to rewrite the expression into sum of simple fractions, according to this rule. If we have a few terms in the numerator divided by one term in the denominator, then we can split this fraction into two fractions. In this case, a over d, plus or minus, depending what sign was here, b over d. And then we simplify within each fraction. Let's observe how this works on particular examples. We need to divide those polynomials by a monomial. Okay, so to perform this division, let's rewrite the question in simple fractions. So 6x cubed over 18xy minus 9xy squared over 18xy. And then we can reduce common factors within each fraction. So we can reduce 6 with 18, leaving 3 in the bottom. We can reduce 1x with 1x in the top, leaving 2x's in the top. Okay, and here we can reduce 9 with 18 and 1x and a single y. So another y will stay in the numerator. Okay, therefore the final answer is, let's see what do we have here in the numerator, just x squared, and the bottom is 3y. Then it's minus, the numerator is single y, and denominator is only 2. Okay, that's the answer. Let's try the second, little bit longer example. Again, we are going to rewrite this question in simple fractions. So each term from the numerator divided by the same denominator. Okay, that will be 12x to the 4y cubed over, and this minus we can actually write in front of the fraction. So over 6x squared y cubed. Then for the next term we can observe that these two negatives we can combine in a single sign. That will be plus. And again 15xy squared over 6x squared y cubed. Finally, positive and negative gives us negative, and it's 18x to the 5 y to the 4 over 6x squared y cubed. Okay, now we need to simplify common factors in each fraction. So in the first one we can reduce 6 with 12, leaving 2 in the top. We can reduce 2x's with those 2x's, leaving another 2x's in the numerator. And we can cancel the y cubed with y cubed. And since we have three fractions and it's so much of cancellations, let's record what do we have left from the first fraction. Okay, that's negative, and then we have 2x squared and there's no y. And the denominator is gone totally, so it's negative 2x squared. That's all. Then it's plus. We can reduce 6 and 15 by 3. 15 divided by 3 is 5, 6 divided by 3 is 2. We can reduce 1x from the top and 1 from the bottom, leaving us 1x in the denominator, and 2 y's from here and there. Again, 1 y is left over. So overall, from the second fraction, we have just 5 in the numerator, and the denominator contains 2x and y, 2xy. Okay, minus, and again, let's reduce whatever we can. 6 goes with 18, leaving us 3 in the numerator. 2x's, after cancelling 2x's, we still have 3 more x's, so x cubed there, and 3 y's. Get rid of 3 y's, another y is left over. So we end up with 3x cubed y in the numerator, and denominator is totally gone, so we really have just 3x cubed y. That's the end. So that's how we proceed when we divide a polynomial by a monomial, single term. However, if we need to divide a polynomial by a polynomial that has more than one term, we need to use long division algorithm. This long division algorithm works nearly the same as long division just for numbers. For polynomials, each term will have similar role as just regular digit in long division of numbers. So let's see how do we divide this polynomial by x minus 2. The polynomial that we divide It's called dividend, and that will be written underneath the long division sign. And the polynomial that we divide by is written in front of this long division sign. That will be the divisor. To understand better this long division of polynomials, let's recall this algorithm in number situation. So let's quickly look at 435. I used exactly the same coefficients here, so we can easily compare the process. And then let's divide this by 2. We ask ourselves how many times 2 goes into the first digit, 4. It goes twice, and we record this answer above the 4. Then we multiply 2 times 2 to figure out how much is already divided out. Oh, it's 4. And then we subtract. 4 minus 4 is 0, so we record this and we drop the next digit. The next digit is 3. And then the whole algorithm starts all over again. So how many times 2 goes into 3? It goes once. So we multiply 1 times 2, it's 2. Subtract and we get 1. Drop the final digit 5 and ask ourselves again how many times 2 goes into 15. Oh, it goes 7 times. 7 times 2 is 14. When we subtract, we end up with 1. So that's the remainder 1. Okay, our division is done. Now let's transfer this process into the polynomial situation. So as I mentioned before, each term of our polynomial will serve like the digits in number situation. Also notice that those terms have another role. They are like placeholders. So in the future, if we write a polynomial in decreasing order of exponents and any term would be missing, for example, if this linear term would be missing, we should still keep this term with coefficient 0, just because we want to keep the columns with the same powers nice and straight. Okay, so if we want to mimic this process, we're looking at the first term of the divisor, only first term, not the whole divisor. And then we're asking ourselves how many times this first term goes into the first term of our dividend. That means we really divide negative 4x squared by x and give the answer above. So it goes negative 4x times. Okay, now the second step would be to multiply our answer by the divisor and find out how much we divided out already. So let's multiply. Negative 4x times x is negative 4x squared, which is what we expected. That's what it's supposed to be. If it's something else, that means we've done some mistake. This first term of the product should be exactly the same as we started with. However, we multiply this negative 4x not only by x, but by the whole divisor. So we also need to multiply negative 4x times negative 2. That gives us plus 8x. And now what is it that we do in the regular long division? We subtract what we actually divided out. Okay, so to subtract the whole polynomial, we need to place a bracket and put a minus in front of it. Okay, how this minus works? Well, this minus really causes changing all those signs. So those first terms will be cancelled, that's for sure, because if we've done our calculations correctly, this first term will always be the same. What's important is to watch the signs of following terms. So we can think 3x minus, remember this minus, 8x, or since subtraction is usually troublesome, we can always convert it to addition, but of opposite term. So I suggest that we write the minus above the plus, but put it in a circle. Why? Because it's so easy to get confused when you start changing the existing sign into something else. So write the new sign in a circle so we really remember that that's the sign that we are taking when we start combining those terms. Okay, let's do it. 3x minus 8x is negative 5x. Okay, so we are at this stage. That's our remainder. And what we do next, we drop the next digit. Instead of digit, we'll have next term in the polynomial case. Okay, so it's plus 5. And the whole algorithm will start all over again. So again, we ask ourselves how many times x goes into negative 5x. Well, it goes negative 5 times. Then we multiply to check how much we divided already. So it's negative 5x as we expected, and negative times negative is positive 10. Again, we need to subtract, so let's place the bracket around subtract, meaning changing this positive sign into negative, and rather than subtracting, we are actually adding. So these two terms are gone, and we have plus 5 minus 10, altogether negative 5. That's our remainder. Therefore, we can say that negative 4x squared plus 3x plus 5 divided by x minus 2 is equal to negative 4x minus 5 with remainder negative 5. But instead of writing remainder negative 5, we can say equivalently plus negative 5 out of the divisor, x minus 2, because the negative 5 was left over, it was not divided by x minus 2 yet. So that's one way of recording the answer to this division. When we work with long division of polynomials, remember two things. Arrange both polynomials in decreasing order of exponents, that's very important, and also replace all the missing terms by 0. That will help you to keep the powers in the same column, so it will be easy to add or subtract. Let's see. We need to find this quotient. So first of all, let's rewrite this question in a long division format. So write the divisor first, and then this will be divided into the dividend. But when you look at the dividend, the second degree term is missing. So the second degree term must be replaced by a 0 term. Okay, let's do it. Negative 3x cubed. Now we can say plus 0x squared because it was missing. 0x squared doesn't change anything. And then plus 4x and minus 1. This 0x squared will serve as a placeholder. Let's see. We'll take the first term and we're trying to fit it into the first term of the dividend. How much is negative 3x cubed divided by x squared? Well, it's negative 3x. And then we multiply. So we get negative 3x cubed, and this times this is negative 9x squared. We have x squared term. If we didn't write the 0 term here, then we would see just 4x in this column, and then we'll be puzzled because we can't combine 4x with 9x squared. They need to be in the same degree column. Okay, so since everything is fine, now what we need to do is bracket around and switch the sign. That means that this sign becomes positive, and then we combine like terms. So obviously the first terms will be gone, and then we have 0 plus 9, so it's just 9x squared. Copy the next term, plus 4x, and the whole algorithm all over again. X squared goes into 9x squared 9 times. Let's record this, plus 9. Multiply back to check how much we divided out. So it's 9x squared. Remember, when we multiply by entire divisor. So both terms, plus 9 times 3x, 27x. Bracket around, switch the sign. Okay, so this sign becomes minus, and we are adding. So this is gone, and 4x minus 27x is negative 23x. One more step. We drop the negative 1 here, and we can try to fit our first term into negative 23x. But what's happened? Well, we can't do it anymore because this x squared is of higher degree than x. So that's where we stop. This whole thing is our remainder. Therefore, we can say that negative 3x cubed plus 4x minus 1 when divided by x squared plus 3x leaves us with negative 3x plus 9 plus the remainder. The remainder is negative 23x minus 1 over the divisor x squared plus 3x. So that's the part that is left over. It wasn't divided yet. The actual quotient is here, and that's the remainder. Notice that this could be written as negative 3x plus 9 minus and then 23x plus 1 over x squared plus 3x. Well, maybe try to justify this to yourself. I hope you see why we just pulled this minus out of the numerator of this fraction. One observation. What can we say about the remainder here? It's not a single number like before. It's a first-degree polynomial. However, our divisor was second-degree polynomial. Generally, the remainder is always of lower degree than the divisor. So that was second. Our remainder could be of first or could be of 0 degree. But it can't be higher than that, because if it would, then we could still divide by x squared and lower it down. Let's look at this example. We have two polynomials that are called p of x, third-degree polynomial, and d of x, first-degree polynomial. Use division to find polynomials q and r such that p of x can be expressed as q times d plus r. I hope you can guess why did I choose those letters q, d, and r. Q stands for quotient, d stands for divisor, and r stands for remainder. So we have this third-degree polynomial p. Let's write it down. 3x cubed plus 4x squared plus 7x plus 4. And we needed to divide this polynomial by the divisor, by 3x plus 3. Okay, let's do it. 3x plus 3. And let's perform long division to find out the quotient and to find out the remainder. 3x goes into 3x cubed, x squared times. Let's multiply x squared by the whole divisor. We'll get 3x cubed, as it should be, and then 3 times x squared, so plus 3x squared. Bracket around, switch the sign, so this plus becomes minus for our addition. 4x squared minus 3x squared is just 1x squared. Copy the next term, plus 7x. And again, 3x goes into x squared. Well, this time maybe it's not so easy, so maybe on the side let's see what will happen. If I divide x squared by 3x, the x is cancelled, but the 3 stays under, so we can record this as 1/3 x. Remember, our answer should be a polynomial, which means the exponent of the variable must be a whole number. And yes, it is. However, the coefficient could be fractional. That's okay. So we write plus 1/3 x. Don't be afraid of fractions as coefficients. It may happen. Okay, let's multiply as usual. 1/3 x times 3x. Oh, that's the same as x squared, because the 3 will cancel 1/3. 1/3 x times 3 is just x. Okay, place the bracket around and subtract, meaning the sign becomes negative for addition. So 7x minus x is 6x. And finally drop the last term, plus 4. Again, 3x goes into 6x twice, so it's plus 2. And multiply back, so we have 6x plus 6. Bracket around and switch the sign, so that becomes negative. Therefore, the 6 is gone, but 4 minus 6 is negative 2. That's our remainder. Okay, so we can write our polynomial in this form. We can say that 3x cubed plus 4x squared plus 7x plus 4, which is p of x, equals the quotient, which is this much. Okay, let's place the bracket here, x squared plus 1/3 x plus 2, times the divisor, which is 3x plus 3, 3x plus 3, plus the remainder. The remainder is negative 2, so we can write like this. And if you want to, you can double check this by multiplying and subtracting 2 and see if the result is the original polynomial. Okay, so we saw that we can divide polynomials. Therefore, similarly as with addition and subtraction and multiplication, maybe we can create quotient functions. Yes, we can. If we take any two functions, f and g, with appropriate domains df and dg, then we can create a quotient function, f over g, that is defined at every single point x as a quotient of our original functions f over g. Obviously, we have to be careful what we are dividing by. We have to make sure that g of x is not 0. So the domain of this new quotient function is similarly as before the intersection of the two domains, df and dg. However, we need to get rid of those points that will make denominator 0. So we exclude all x values that will make the g function equal to 0. Okay, using this definition, let's practice on the following functions. F of x is defined as x squared minus 4 quadratic function, g of x is a linear function x minus 2, and h of x is a linear function negative 2x. We need to find the following expressions. The quotient f over h at x. Well, according to definition, that's the same as f of x over h of x. But what's f of x? Here we have the formula x squared minus 4. And h of x is negative 2x. So this is the new quotient function f over h. Now in the B question, we need to figure out what's the domain of the quotient function f over h. But in order to do that, we need to know what's the domain of f function and h function. So let's write down on the side what's the domain of each of those functions. Maybe we can refer to them later. Domain of the function f. Oh, that's a polynomial, so the domain of any polynomial is all real numbers. Let's look at g, that's also a polynomial, and h is a polynomial, so basically domain of all of these functions separately is all real numbers. There's no problem for any of them. All real numbers. However, to find out domain of the quotient function, it's not only that we are taking domain of f and h, and intersect them. Obviously the intersection is also all real numbers. But on the top of it, we have to subtract those points that will make the h function 0. So when h function is 0, well, negative 2x is 0 for x being 0. So we have to get rid of 0 from the domain of the quotient function. Therefore, the overall domain of the quotient is all real numbers except for 0, because 0 will make this denominator 0, which is not allowed. Okay, let's look at example C. Here we need to figure out what is the quotient function f over g. Again, according to the formula, that's f of x over g of x. F of x, as before, is x squared minus 4 over g of x, which is x minus 2. So, at this moment, you may observe that in the numerator we really have difference of squares. And remember from special formula, difference of squares, that's the same as x minus 2 and x plus 2. We can actually factor it. And in the denominator we have x minus 2. So what can you say now? We have the same factors. Well, therefore we can cancel them. Okay, therefore this quotient function is really the same as just linear function x plus 2. Is that true? Maybe. According to our simplification, that's supposed to be equal just x plus 2. But let's check the domain of our function. Domain of f over g is the intersection of the domains of f and g, which is these two, but intersection of all real numbers with all real numbers is also all real numbers. However, we need to subtract those points that will make g function equal to 0. When g is 0? Well, g is 0 when x is 2. Therefore, we need to get rid of the 2. The 2 can't be taken. Okay, so let's look at this. Since our quotient functions equal x plus 2, and x plus 2 is actually a linear polynomial. However, we know that domain of any polynomial is all real numbers. But domain of our function is not all real numbers. It differs just because of this one single number 2 that had to be excluded. So how to explain this? Is our quotient function really the same as a line? Or not quite? Well, the answer is yes, it is, but in this domain. That means it is a line, except at number 2, because this domain is actually calculated for this expression, not for the final expression. Therefore, these two expressions are equivalent only in that domain. They are not equivalent in all real numbers. They are equivalent in all real numbers, but not 2. Now let's calculate this expression. Will we have a function, or we will have a single value? Well, since this function is evaluated at specific point, the result of this expression is actually a single value. Let's calculate this. It will be f of -1 over h of -1, which means we need to follow f function. That tells us take the input, square it, and subtract 4, over h function. That tells us multiply the input by -2 and calculate. So we have 1 minus 4, that's -3 over +2. The final answer, -3/2. That's the value. Maybe the next one you can do it on your own and pause the video and come back in a second when you finish. That will be f of -1 over g of -1. F of -1, as before, is taking -1, square it, and subtracting 4. G of -1 is taking -1 and subtracting 2. So we have -3 over -3. That's equal to 1. No problem here. Okay, let's see this value. Here we need to calculate f of 0 over h of 0. So for f of 0, we replace x in the f function by 0. So it's 0 squared minus 4. That's really -4. But h of 0, when we replace x by 0, we have value 0. So, what's going on? We can't really divide by 0. That's undefined. Well, we should actually expect this, as 0 does not belong to the domain of f over h. Here it's our domain. Okay, that's not in domain of f over h. That's why the value of this function at 0 doesn't exist, is undefined. Let's see the next example. We need to calculate f of 2 over g of 2. So that's a quotient f over g at 2. Well, can you predict what the value will be here? Let's check the domain of this function. The domain of f over g was all real numbers but not 2. However, this time we're trying to evaluate this function at 2. Well, this value can't exist because it wasn't defined at 2. But let's see where's the problem. F of 2 is 2 squared, which is 4, minus 4. Okay, that's 0. And g of 2, if I plug it in 2 for x in g function, it's 2 minus 2. I have 0 over 0. That's definitely undefined. We can't divide by 0. Notice that if I use this function, which we calculated as equivalent, so when I evaluate this function at 2, I will get a value. I will get perfectly fine value. It will be 4. How come I can't get this value by using the original formula? Well, that's because these two expressions are not equivalent when x is equal to 2. They are equivalent for any other real number, but not for x equals 2. So our quotient function f of g is not defined at 2. Again, the 2 is not in the domain of f over g. Okay, one more example. G over h at 1/2. Okay, so that's g of 1/2 over h of 1/2. Let's follow the g function. It tells us to take the input and subtract 2. So input is 1/2 and subtract 2 over h function. It tells us multiply the input by -2. So it's -2 times 1/2. Okay, so we end up with complex fraction, but we know how to simplify it. We can reduce the 2's, and then 1/2 minus 2 is -1.5. So it's -3/2, we can say. Because 2 is like 4/2. 1 minus 4 is -3/2. Over, and here we really have -1, so overall answer is actually 3/2. Finally, this question we'll write a little bit farther. H over G at 3/2. So H at 3/2, which is multiply the input by -2. So 3/2 times -2 over G at 3/2. And G tells us to take the input and subtract the 2. So 3/2 minus 2. Okay, now in order to simplify this, we can reduce the 2 here, and we can convert the 2 from the bottom into 4/2. So 3/2 minus 4/2 is -1/2, and in the top we have -3. Two negatives makes it positive, and to divide by a fraction means to multiply by reciprocal, so it's really the same as 3 times 2, which is 6. Final answer. Okay, so that's how we deal with quotient functions.